Hi guys, good morning. Happy Monday or Tuesday, whenever you're watching this. So first, before I get started with anything, I just wanted to let you know that I am working on getting something put together for a little more practice of the conversions between mass and moles and atoms. I think that just based off of what I've looked at with the assignments and then seeing how kids are doing in class, I'm assuming you guys are probably on the same level, that we probably just need a little more practice. I've got about 80% that really get it and we're good, and then we got about 20% that still need some help. So that's fine. A little more practice never hurt anybody. So today we're going to pick up where we left off, and it will kind of come together at the end of the lesson. So I know we left off at the electromagnetic spectrum last class, which is this slide. So we have like our different visible lights right in the center, but then there's all these other types of waves on either end of that spectrum that we can't see, but we know that they exist. So we knew that the longer waves were lower frequency, and that these were lower energy. And then you come down here to this side, the gamma rays, they are higher frequency and higher energy. Visible light has its own little visible spectrum, and we kind of went through here, and you could look at the different frequencies and wavelengths related to that. And then we did talk about some of these formulas that are in the bottom left corner. I don't want to move my mouse over there because the little menu at the bottom will pop up again, but you can see that in the bottom left corner. We're going to reference that again today, especially the formula that Planck is using. So Planck's formula was energy is equal to Planck's constant times the frequency of the wave. So we're going to use that today to talk about kind of like where electrons actually fall or where they should belong within their own like orbitals. And I know that that's terminology you've used before. You guys are familiar with like Bohr's model of the atom, which we can just get started on that. Okay, so we know that this is Bohr's model of the atom. Okay, so we have a nucleus in the center. The nucleus is made up of protons and neutrons. And then we know that the electron's going to fly around on the outside. But there's been research done that shows us that there's a specific place that different electrons kind of stay, and it has to do with their energy that they have available. So when we'll talk about what these N stand for here in a little bit, but if you notice this formula again, this is Planck's formula. Okay, so we have the change in energy, so a delta just means change. So change in energy is equal to Planck's constant times the frequency. Okay, and this little wiggle line going out is showing the energy that's being given off. So we talked about this last time with the part of the photoelectric effect. So let's say we energize this electron, and now he's out on the third level, and that's not really where he belongs. So once he uses up that energy, he's gonna jump back down to his ground state. So he's at the excited state. He's coming back down to the ground state. When he comes back down to the ground state, he's going to give off a photon of light. So that's what this red squiggle line is representing. So once this electron comes back down to its ground state, it's going to release a photon of light. You can tell what frequency of light that's going to be or how much energy you're going to get there based off of this equation and what else we know. Okay, so we know that this is going to be Bohr's model, and it shows electrons in like just straight orbitals, right? Just like a circle going around. And we'll talk about that because that changed with a little more research. So we did talk about this here. So this formula is describing the energy released here. So we know that this initial like Bohr's model, like when this was coming out, this was in the late 1800s, early 1900s. So we're talking like 1900, 1905. So about 20 years later, this researcher came by. We pronounce his name De Broglie. It looks like Broglie, but it's not. So De Broglie came by in 1924 and hypothesized that electrons could also behave as a wave particle, which if you remember, Einstein had said that photons of light behave as both a particle and a wave. So he is working off the same theory basically, but he's making it a little more specific, saying that it's not a photon, it's not a particle or a wave, it's a wave particle, that these particles travel in waves. And I'll show you an example of that in a second. So he basically was saying that electrons are waves that are confined to a specific space around the atom, and that they have to have certain frequencies. Those waves have to have certain frequencies to exist in that orbital. So this is what he's talking about. And I know this looks a little complicated. This relationship here, you don't have to memorize this formula or anything. It's a mathematical representation of what they're talking about. So they're saying that the wavelength, which we know lambda is the wavelength, is basically equal to the frequency of the wave. Okay, so the position of the electron within the orbitals. Sorry about that. The position of the electrons within these orbitals depends on their frequency, and you can see that a little better down here. So I'm going to have to not point at this so that that little menu doesn't pop up. But if you look at the first one on the left-hand side where it says n equals 1, the n's just describe basically which orbital you're talking about. So n equals 1, you can see that that's just one circle. It's a regular shaped circle at the bottom there. It shows the wavelength. It's a very long wavelength. There's only one wave cycle in that wavelength for N1. N2, you can see there's 2 full wavelengths happening, and you see that pattern increases, right? So as we go across, we're increasing the wavelengths. So you're going to get a different pattern. Basically, that's what all these like shapes at the bottom are, showing you the different patterns that the waves or the electrons are moving in. So you can see there that it's basically just a sideways representation of what these wavelengths would look like. So as they're moving along, we're saying that these electrons are moving in their own little wave patterns, and they have to have a higher and higher frequency to be able to reach the outer levels. Okay. So then a couple of years later, we have Heisenberg, which I know was part of your research. So Heisenberg came up with his uncertainty principle. So he was trying to find the location of an electron in his research. He was trying to figure out like where exactly are these things at, because up until this point, no one really knew. They were just making up theories saying that, well, we really think that it behaves like this, and it's probably in some kind of orbital, but they didn't really know what that meant. So here we have Heisenberg was trying to figure out where an electron was, and in his research, he figured out that if you try to figure out where it is, you're actually moving its position, or it's no longer where it was. So what he was doing was he was like shining light, basically like photons of light, into an atom to try to get some visual. Okay, so it's kind of the same idea as if you shine a flashlight out into the dark yard, like at night, you shine a flashlight out into your yard, you see what's there because the light's bouncing back. It's reflecting back into your eyes, right? So we see like the swing set in the backyard because you shined your flashlight over there. Now that light is reflecting back and you are interpreting it in your brain. So that's kind of the same idea what Heisenberg did here. So he shined small beams of photons into an atom, trying to find these electrons. And he figured out that the act of actually doing that was changing the electron's position. So if you can imagine this tiny beam, and we know that light acts as both a particle and a wave. So if you think about them as particles, you're basically like shooting these tiny particles at an electron, which is very, very, very small. And so these photons of light were like bouncing off these electrons, basically. So by the time that image got back and you were able to interpret it, the electron was no longer where it was when you hit it with the photon of light, because you bounced it off into another direction. Even if he found that even if he did hit the electron just right and it didn't bounce it out of its orbital, the electrons are moving so quickly that it didn't matter. Even if you caught it at that instant, the electron had since moved on by the time the image got back. So this was his uncertainty principle. This here was his principle, that neither the position or the velocity of an electron can be known at the same time. So you can't know where an electron is and how fast it's going at exactly the same time. So if you figure out how fast it's going, it's no longer in the same position. And if you figure out what its position is, you have no idea how fast it's going. So this was his principle that he came up with, which seems kind of random right now, but it'll kind of all play together as we work through here. So then we have Schrodinger, which I know you probably know Schrodinger by Schrodinger's cat. He's neither dead nor alive. But he also had some research that went into the atomic model, okay? So he hypothesized that electrons have a dual wave particle nature, that kind of the same way de Broglie did, so that these are, it's not just a photon, it's not just a particle, and it's not just a wave. So his ideas helped lead to quantum theory, and quantum theory mathematically describes the wave properties of electrons. So we talked about de Broglie's theory said that our electrons move in waves, so we're building together. So this is how science works. It's slow sometimes. It takes many years to build on ideas until we get to somewhere where they're accepted, but eventually we'll get there. So here we talked about the quantum theory, and then we know with Heisenberg that there's only kind of a probability or a guess of where an electron might be located, and you know that it can equally exist and not exist at all possible locations. So that's here. Heisenberg's uncertainty principle was that we can't know where an electron is and how fast it's going at exactly the same time. So Schrodinger built upon that, saying that there's really only a probability, like we can mathematically come up with a probability of where an electron is located. So same kind of idea as Schrodinger's cat, that the electron is equally exists and does not exist at all possible locations at all times, because we can't ever know. We can't ever know exactly where an electron is. So I'm not going to play this video right now in interest of keeping this video short, but this is a really good video that explains Schrodinger's cat experiment and how that is related to all of this. So when you guys are done, or if you have another minute later, please come back and watch this. It's in the slides. So now that we had the quantum theory, we know that we can mathematically calculate maybe how fast an electron is, where it might be. We know now that electrons don't travel in these neat little circular paths around the nucleus like Bohr had initially suggested. So I know that the Bohr model, which you can see here in this picture, the Bohr model is what's in every science textbook. It's kind of what we work from, but it's kind of a loose translation of what's actually happening. So we do know that electrons do exist in orbitals. Okay, so it's not just a ring, but an orbital, and this picture down here represents that a little bit better. So it's more like a sphere. So an orbital is like a sphere around a certain area of the atom, and electrons exist within that sphere. So they might not be going in a perfect circle like east to west, going straight around. They could be going in many different directions, but they're going to stay within that energy level of that orbital. They have a specific area that they exist in unless they gain or lose energy. So again, another video that is beneficial. This does a good job of explaining kind of like why these electrons would need to move out into a different orbital. But this picture down here, and we will talk about this a little bit more later on in the year too, but this shows nicely, we're going to go through it, kind of like where all these electrons can exist. So each level is showing a different orbital. So level 1, this would be like N1. This is like your first orbital, only 2 electrons can exist there. On the next one, you have 3 different shapes, right? 2 electrons can exist in each shape. So in N2, 6 electrons can exist here. And then you can just keep going on. I think you guys can understand that pattern. Okay, so when we get down here, we've talked about quantum theory being able to mathematically describe what's going on with the electrons. The quantum numbers will specify the properties of the orbitals and its electrons. Okay, so the quantum numbers are going to determine which energy level and the shape of the orbital. So as N increases, so does the electron's energy and distance from the nucleus. So this purple piece down here is important to know. And this is N, it's kind of like what we've been talking about, referencing this whole time. So if you go back and look at any of these diagrams, they all have like N1, N2, because that's representing the next orbital. So you will see, again, this is Bohr's model of the atom, it shows the rings, but we know that this is the simplified version of what's really going on. So we know that there's really all this is happening. Okay, so this is difficult to represent in layers. So imagine layering all of these photos on top of each other and then trying to see what's going on is very difficult. So that's why you still see this Bohr's model of the atom, because it's easy to describe what each energy level contains. Okay, so we know that like on N1, so N1 is going to contain 2 electrons. N2 would have 6, and you keep on going up. So just understand that even though you see this a lot, that we do accept this method more. Okay, so as we talk, you'll see like these described as N1, N2. Just know that that's the different orbitals that it's talking about. And as you get further away from the nucleus, you have to increase your energy. Okay, so it's kind of like, let's go back here to this with de Broglie. So N1, so these are talking about this is the first energy level. So this is closest to the nucleus. This one's the next one, third one, fourth one, fifth one. So by the time you get all the way out, if you have something that has a 5th orbital, you are talking about a lot of energy. That electron has to have a lot of energy to exist on that energy level. Okay. So this is just another way to look at this. It kind of it does a pretty good job of showing the different layers and kind of why we use Bohr's model to represent an atom, even though that we know that that's not really what it looks like. So we're coming down to the end here. So if you have this, we know that atoms exist. They're like 3-dimensional, right? So they're not just an X and Y plane, they have like a Z plane, which goes like straight through the middle. So if you're looking at this kind of like a jack, hopefully you guys know what jacks are, maybe not, it's an old game, but it's kind of like a jack there. So you have a 3-dimensional plane we're talking about. So the first orbital, okay, so we're going to pretend that this little blue dot is our nucleus. So our first orbital would be this, and you can see it's a sphere. So these electrons are moving anywhere within this sphere, but they stay within this sphere. They're not going to just fly out here somewhere. So this is the 1s orbital, which this is talking about electron configuration, which we'll do, I think, next class. So ignore the 1s for right now. That'll come together when we start doing electron configuration. But know that we're here on our first orbital, okay, and it has 2 electrons because that's all it can hold. Then we add another orbital, okay, so this is 2s, so it's 1 more orbital on top, okay, so we still have the other orbital inside. Now we have another orbital on the outside with other electrons. Now we're in 2p. So this is the next step. You get this figure 8 kind of motion here. So we still have these other orbitals inside. Keep adding. This is the whole p orbital. So this is basically like 2 energy levels. And you can see hopefully how this is getting more and more layered and complicated. So we're going to keep filling these up with electrons. Then you would add another one. So within that, you can see now all these layers. You have all these layers of areas where the electrons can exist. And in order to get out to these outer layers, they have to have more energy. So that relates back to de Broglie's model. Okay. Sorry about that. I had to pause it for a second. All right, so we kind of talked about how these layers look. So in general, we're still going to want to represent these electrons on rings because that's much easier to see and describe than this. Okay, this is what it actually looks like, but this is very difficult to write down. It's very difficult to keep track of because you have things in 3 dimensions. So to describe the location of electrons, we still use the Bohr models for that. So the Bohr model still is going to give you kind of an approximate location and energy for all of your particles. We know that as we move further away from the nucleus, we're going to get more and more energy. So within these electron shells or orbitals, we've talked about them, they can only hold a designated amount of electrons. Okay, and this table here is important. Okay, you're going to want to know which ones hold how many. So your first electron shell, so your innermost orbital here, is going to hold 2 electrons, and that's it. Okay, so if you're drawing electrons on these rings, gosh, so many bells this morning. If you're drawing electrons on these rings and you get to 2, you can't put any more on this ring. The next one has to go on the next ring. Okay, so your second orbital will hold 8. The third orbital will hold 8. Once you get out there, if you have a really big one, you might get to 18 on the next one, 18, and then 32 and 32. We won't do a whole lot of those really, really big ones. Most of the bonding that occurs happens in the first couple of periods on the periodic table. So we'll basically work probably within like 1 to 4 rings, but you do need to know this pattern. Okay, so it's 2 and then 8 and then 8 and then 18 will be kind of our pattern there. Just throughout the years, I have come to the conclusion that some of you guys got some practice with this in 9th grade and some of you did not. So if you guys remember this from 9th grade, awesome. If you don't, we're going to work on it. So what you want to first figure out is how many electrons are in that atom, okay? So if you look at silicon on the periodic table, you'd see that it has 14 electrons.
Please stand for the pledge.
Okay, sorry about that. I paused it for the pledge. All right, so you want to figure out first how many electrons there are. So if this model here is looking at silicon, you look at the periodic table, you know it has 14 electrons, because if we're talking about a neutral atom, it has 14 protons, 14 electrons, because that's the atomic number. So you start on the innermost shell, you draw 1 ring around the nucleus. We know that only 2 electrons can fit here, so that's all you can put on this. You do want to space them out. Like, these would be better representations of how to space out your electrons a little bit. But so if we spaced out these electrons, we'd have 2. That's all that fits there, because that's all you can put on it. So we know we're going to have to move to the next ring. So the second ring we know can hold 8. So we have 2 here. So we're going to add the next ones on this. We're getting to 14. So I have 2 here. I'm going to add 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now there's 8 on this ring and 10 all together. We need to get to 14, so we're going to move on to the next ring and add 4 more out there. So you're going to start on your innermost shell and kind of like work your way out. You're going to fill them up according to this chart, and then make sure you stop when you get to the number of electrons that you're trying to get to. Okay, so I want you guys, you can practice this. You can pause this for a second if you want and try it on your own. Okay, so this is what the carbon, would look like. Okay, so you have carbon in the center. You can just write the element letter. You can just write a C and start drawing your rings. Okay, so I have my nucleus of carbon here. I have the first ring is going to hold 2 electrons. And the next ring is going to hold another 4, because if you look on the periodic table, carbon has 6 electrons. So only 2 can fit on the first ring. On the next ring, we're going to add the other 4, and we're done. Okay, this one all popped up at one time, sorry. So can't really practice this one, but if you have the Bohr model for potassium, okay, potassium's a little bit bigger because it has more electrons. So if you look at potassium, shoot, I can't even see that from here. I can't see it from here, how many it has. I think it's 19. So if we have 19 electrons here, you're going to have 2 in the center, 8 on the next ring, 8 on the third ring, and then the last one would be by itself out here. Okay, so hopefully this makes sense, that you're working from the center, working your way out, and you fill them up with however much they can hold, and then keep going. Okay, so the last thing we're going to talk about today is Lewis dot diagrams. So these are going to use your valence electrons only, which are going to be the electrons on that outermost shell. So these are going to represent electrons involved in bonding. So when we start talking about, the whole reason we talk about electrons so much is this, basically. So when we start talking about bonding, you can see that the way this is arranged here, it has like a specific shape, and so does this one. We will eventually start talking about the Bessemer shapes, the shape of molecules. So this will be important in understanding how to create those different shapes later on. So when you have an electron, when you have an atom, you have all these electrons flying around. Only the ones on the outermost rings are actually involved with bonding. Okay, so they're either going to give up an electron or they're going to gain an electron to form a bond, which we will talk more about later on. But okay, sorry about that. I had to pause it for a second. I get busy morning in here. Okay, so when you're talking about these Lewis dot diagrams, this is basically like a condensed version of your Bohr models, okay? So with the Bohr models, you're representing all of the electrons all the way out to the edges to show kind of how the energy is distributed throughout the atom. The Lewis dot diagrams are abbreviating that so that you're only looking at the valence electrons, and these are used for a different purpose, basically. So the Bohr model diagrams, these are longer, they are more involved, basically. You're adding rings and dots and all this stuff, but this is important for showing the electron configuration, so how the electrons are arranged within the atom. So that's kind of like looking at one topic. And then the Lewis dot diagrams are going to be used for bonding. So this will be important in a different way. It's just looking at it, representing a different way. So when we look at these, we're going to be looking for just the valence electrons, the only ones that will be on the outermost shell. And when you add your dots to your Lewis dot diagram, there's a total of 8 that can be represented here. So you can have a total of 2 on each side of this. Okay, so you can put like 1, 2, 3, 4, 5, 6, 7, 8. When you draw them, there's a specific way that is correct. So if I had carbon has, so let me go back here. Okay, carbon has 4 valence electrons. Okay, so there's 4 on the outside. Valence just means the outermost shell. So we have 4 on the outside. So carbon would have 1 dot in the top left corner. We'd add another dot on the next side. You add another dot on the next side, and then another dot on the next side. This is the pattern. This is how you have to fill these out, okay? So you start on the top, and you put 1 on each side, and then you can come back in and fill them in as you need to. There should never be more than 8 dots on a Lewis dot diagram, ever. So how do you know? Like, how do you know how many valence electrons there are without having to write an entire Bohr model with them? So there's an easy way to do that. If you look at your periodic table, you look up here, you have group numbers along the top. Hopefully you're familiar with those. So you have group numbers going along the top here, 1 through 18. You are using this as a clue to tell you how many valence electrons there are. Okay, so if you're in group 1, everything in this group has 1 valence electron. Everything. Okay, so if I'm looking at potassium, 1 valence electron. So you have 1 dot on a Lewis dot diagram. Okay, so you'd have like 1 dot right here. Everything in group 2 has 2 valence electrons. We skip the transition metals for now because those have their own set of rules, and they bond differently. So the electrons, it becomes like a different method to look at those. So we're gonna, because these are all like metals and it's like a sea of electrons. So the way they bond is different. So we're gonna skip 3 through 12. Okay, that you won't have any of these for to draw valence electrons for. So 1 and 2 is just 1, 2. Then you get it here, and it's 13 through 18. Okay, so remember we said that you can't have any more than 8 valence electrons. You're not going to have any more than 8 on a Lewis dot diagram. So you look at this is 13. Drop the 1 off of it. All of these have 3. Okay, so every single one of these is going to have 3 valence electrons to bond with. All of these would have 4. Everything in this column, all these would have 5, 6, 7, and 8. Okay, and when you get to 8, these are your most stable atoms. These don't bond with anything because they're full. Okay, they're not missing any electrons. They're full. They have 8 valence electrons. So you guys may not have a printed out copy, but you do need to know kind of like what groups versus periods are. So if you're using the electronic version of the periodic table, that's fine. Just understand what these are. So groups are going to be your vertical columns. So you're up and down. These will be the groups. And then the periods go horizontally, which we'll talk about the names for all these later. Not right now, but just know that when I'm talking about groups, these groups, I'm talking about vertical, up and down. Okay, so here's some more examples if you want to pause this for a second and give this a try. So if you draw the Lewis dot diagram for calcium, you would want to look at your periodic table, figure out how many valence electrons it would have. So calcium is in group 2, so it's going to have 2 valence electrons. So you're going to write 1 at the top and 1 on the side, and that's it. You're done. Okay, so you would not want to put 2 together at the top because they do need to go in this order. And this will be kind of important later on when we're talking about bonding and drawing these out for bonding. You'll be drawing the Lewis structures for bonding too. So sometimes these can be moved if you have a certain shape of a molecule being formed, but most of the time you'll leave them in this like fashion. That's why we write them like that. Next one, if you want to pause it. So you're going to draw the Lewis dot diagram for bromine. So if you find bromine on your periodic table, where is bromine? Okay, so I'm looking at a periodic table all the way across the room. So it looks like it's in group 17. So you're going to have 7 valence shell electrons. So you would start, make 1 dot on each side. That's only 4, right? So you go back in and add 3 more. Okay, so now we have 7 valence electrons for this Lewis dot diagram. And that's it for today. So we will talk about electron configuration next class, and that has to do more with the orbital levels. But today, basically just wanted to get down the basics of drawing your Bohr diagrams, okay? So representing the electron configuration within each orbital, and then also just focusing on valence electrons. So if you guys look under the assignment tab, you guys have some practice over Bohr models, like drawing your Bohr models and your Lewis dot diagrams. So if you guys get that finished up for today, you guys will be good to go. So I'm going to make it optional if you, I'll put it up there. So you should still have access to the in-class activity that we're doing. You are cutting out, you would have to like print it and cut it out. So I think it's a good practice, but I think you guys also have a lot going on trying to learn this on your own and do the homework for it. So I'm just going to assign the homework assignment to you guys. If you want to do the lab or the activity that I have the in-class kids doing, you're welcome to do so. It just is a good practice, and you can send it to me and I'll check it, but I'm not going to require that you do that because I'm sure you guys have just way too much going on right now anyway. So get the assignment done. Let me know if you do have any questions. Don't forget to be checking the answers in the agenda for anything. So anytime we do practice, I always have the answer key posted in the agenda. So double check your work there. We will be having a quiz maybe this week, maybe early next week. I haven't decided yet about the conversion. So like I said, I'll get some more information out on that today. So get your stuff done. Let me know if you have any questions, and I will talk to you later.